Come on in, everyone. All right, it's about time for classes to start. So, does anyone have any questions before we get started? We got a ton of people here already, so that's good. By the way, I should be making the next test available tonight, so just be prepared. It's probably going to be uh, available tonight. The practice test as well as the online test will be available tonight, and you'll have until Sunday at 11:59 p.m. to get that done. So make sure you don't miss that one. Tonight we're actually going over chapter 6, and really I only spend pretty much one day doing that, but I wanted to get you started on it. So again, does anybody have any questions on any previous material before we go getting started? More people in the waiting room. What's it? Oh, there it is. Yeah, it looks like everybody's finally out. So I was just telling everybody there's going to be a test, the next test, which I think is test 4. Uh, that should be on, I think, 5 and 6. As I said, I'm planning on opening it up today. It'll probably be open. It'll probably be due. The online test will actually be due Sunday at 11:59 p.m. I might push it back just to make it to Wednesday. But really, chapter 6 is going to take today, and that's pretty much it. You've got plenty of examples that you can see on my YouTube channel as well as in your book. I'm just going to give you the basics and explain to you how stuff's done. So one more time before I get started, since I just let about 6 more people in. Anybody have any questions about anything in the past? Any questions about anything before we get started?
I haven't took the exam one.
Uh, what did you say about the exam? It was a little quiet.
I haven't taken it yet. But I've
Oh,
been needing
oh, gotcha. This is who was talking?
the
Was there?
shard.
Okay. I thought I remember getting the email and setting it up, but I'll definitely do that. Let me write this down real quick. Actually, I'll tell you what. Was it test 1 on chapter 1 and 2, or was it test 2?
Um I'm not sure, but it was last week and I didn't know what to do. So I
I got you.
emailed
Don't
you.
worry. It's that I probably missed something. I'm looking at grades real quick and see if it's test 1 or test 3 so I can remember. Uh, looks like I'm looking at it. There you go. Test 1. That's chapter 1 homework. So, okay. Oh, that's what it was. I remember now. You seem to have taken the 2 online tests, but you didn't take the face-to-face test. That's a little bit more of a problem. You'll need to go to a testing center to do that, but I can set that up for you. So I'll tell you what, I'll send you an email after this is done, and that should do us. Let me get off this before I get into some mess by accidentally showing everybody's grades. All right. So thanks for starting for that, and I apologize for the delay and all that good stuff. So what we're starting to talk about is chapter 6, and in chapter 6 we're starting off with Newton's law of gravity. And basically what it was is, if you read Newton's Principia, which is a long, long book, but it's and it was originally written in Latin. The first translation was made to French by Madame de Châtelet, who was a brilliant 16-year-old girl. I think she was 16 or 17 when she translated it, but she later took on Voltaire as her personal boy toy, if you will. So you can imagine how brilliant a young lady must be if she's using Voltaire as her personal boy toy, and how, obviously she was intellectually uh, stout as well, just for being able to interact with him, as well as him being able to interact with her. They're both very bright people. But she translated to French, and in his Principia, he said basically something along the lines of he was at his apple orchard when he looked up and saw an apple and the tree in the distance. I mean, the moon in the distance, and he realized how they were similar. Specifically, what he meant was when the apple becomes sort of engorged with water, it's basically going to become so heavy that the stem can no longer hold it. The stem will break, and what we now know of as gravity will pull it to the ground. And that, of course, causes it to accelerate downward, which we were able to discover thanks to Galileo, who took the time to study motion on inclined planes because it was too complex and too fast to study by literally dropping it vertically. So he had to use inclined planes just to slow it down to see what was going on. So Newton argued, well, if it is the same thing, then he knew that the acceleration of gravity at the surface of the Earth was 9.80 meters per second every second. And that was one Earth radius from the center of the Earth. And he also knew that the moon was 60 Earth radii from the center of the Earth. And just so you get it straight, if the Earth is about 4 centimeters wide, then the moon is about a half a centimeter. And I don't want to say 4 centimeters, I'm talking 4 centimeters in diameter. Then the moon is about half a centimeter in diameter, and it will be, in fact, 1.20 meters away. So it's really, really a huge distance. And hopefully that gives you a better appreciation for the Apollo missions that went to the moon. It's really, really a long trip. In fact, it takes light over a second to get there. So what Newton did was Newton said, well, I think that's the case, but I'm not really sure. So he wanted to verify it. And what he did was he realized exactly what the acceleration of the moon would have to be if in its normal path it was supposed to be deviated so that it could go in a circle, essentially a circle. It does get closer sometimes, and therefore it's somewhat of an ellipse, but the difference in the nearest and the farthest is so minuscule compared to the total radius that it is essentially very close to a sphere, or excuse me, very close to a circle. So the centripetal acceleration, the centripetal acceleration required for an object to go in a circle, we know because we just learned it, is AC is equal to V squared over R. And what we know is for the moon, the velocity of the moon was such that it would go the circumference of its orbit, which is 2 pi times R, in a period of t. So that velocity is 2.
Are you writing?
Yeah, I'm getting ready to share that. I did forget for a split second though. I just had remembered. But yes, I am writing, and I'm trying to hide it from you because I don't know why. All right. Here we go. Oh Lord. Okay, got that. Okay, now this one, there you go. Now it's coming up. Okay, so 2 pi. Now I need the distance to between the center of the Earth and the center of the moon. That turns out to be 60 Earth radii. So I'm going to write it as 60. And then I'm going to I'm going to record the radius of the Earth. And the radius of the Earth is 6.378 times 10 to the 8th. No, that's not right. That's not it at all. Oh yeah, that can't be it. So the Earth's radius, I'm actually pulling this up, of course, came into the one place where it's saying everything in friggin' miles. 6.378. The Earth is almost, but not quite a perfect sphere. Its equatorial radius is 6,378 kilometers. but its polar radius is 6,357. So they differ a little bit. So it's 6.378 times 10 to the 6. That's what it is. So 378 be 10 to the 30. Yes, 6.378 times 10 to the 6 meters. And then the time, the actual period is 29.5 days. And then, of course, 1 day is equal to 4 hours. And then, of course, 1 hour is equal to 3,600 seconds. So we can figure out that the velocity of this is 2 times pi times 60 times 6.378 e to the 6 meters. Okay, just for the record, in case you want to know what that R is, that 60 Earth radii. This is actually kind of handy, so I'm going to say 60 times the radius of the Earth. And this is the astronomical symbol we use for the radius of the Earth. That's 3.826 times 10 to the 8 meters. And the reason why I give you that is I want you to understand the speed of light is 3.0 essentially times 10 to the 8th meters per second. So it takes light a little bit over a second to travel from the moon to us. So I just wanted you to know that. But anyways, I have this figure 2 times 3.14159 times 60 times 6.378 e to the 6. That gives me the circumference of the orbit. Then I'm going to divide that by parentheses 29.5 times 24 times 3,600. And all that gives me a velocity of 900. I don't know why I'm switching to blue. Oh, I do know why. Of 943.4. I'll call it 0.36 meters per second. That's how fast it's going. And it's nearly circular orbit. So now that I use that, I can say that AC is equal to 943.36 meters per second. Now, I should point out that I was using 4 sig figs on everything. So really, at least that 6 is unknown. I think the 60 really is only known to 2. So I should probably at least only say it's 3 sig figs. But now I've got to take that and square it and then divide it by, again, that radius of the orbit, which is 3.826 times 10 to the 8th meters. So if I square this and then divide it by 3.826 e to the 8th, that gives me 0.002, roughly that. We'll call it 0.002 and leave it at that. Now, Newton actually took and considered what if the force that attracts the apple to the Earth, and therefore the same force that attracts the moon to the Earth, what if it's a 1/r² force? That means that, for instance, if you move instead of 1 Earth radius from the surface of the Earth, which is where things on the surface of the Earth are, to 2 Earth radii, you'd expect the force to go down by a factor of not 2, but by a factor of 2², which is 4. If you go to 3 Earth radii, you expect it to be 3², or a factor of 9 less. 4 would be a factor of 16 less. 5 would be a factor of 25 less, so on and so forth. But in this case, we're going a factor of 60 less. So the gravitational acceleration at the moon, if we're right about that, would be 9.80 meters per second every second. divided by 3,600, because 60 squared is 3,600. Just like when I doubled the distance, I divided it by 2 squared. When I tripled the distance, I divided it by 3 squared. So if I do that, I get 9.8 divided by 3,600, and that gives me about 0.002 roughly. Now, really, the difference is that I really should be doing a little bit better job than the 29.5 days. In fact, the period of the moon's orbit is a couple different ways depending on how you look at it. The 29.5 days is basically the time for it to go from a particular constellation to that same constellation. So that's called the sidereal period. And sidereal means star. So it's a sidereal period. So for instance, if you looked up and you saw, let's say, a crescent moon, and it happened to be in the constellation Gemini, like this, okay, and you waited till it happened to be in Gemini again, then what would happen? Of course, it would be probably in a different phase. So maybe we'll say it's almost to a quarter moon, but in this case, again, it would be like that, and this time would take 29.5 days. Now, if you take it from new moon to new moon, that's 27.3 days, and that's from new moon to new moon. So we really, to be as close as we want, this number actually turned out to be 0.00272, whereas the first one I calculated turned out to be 0.00232. So this one was 272 and this one was 232. But you see, they're definitely among the same order of magnitude, basically. When Newton covered it, he actually got close enough where it was a couple digits, and he was felt very confident. So at that point, Newton's the only person on planet Earth that knows, why the moon orbits the Earth, why the Earth and all the other planets orbit the sun, why the Galilean moons orbit Jupiter, and so on and so forth. And in fact, he went on to postulate, and remember, in the time of Newton, we didn't have vectors. So you had to state everything sort of explicitly to get down the vector property of it. And again, like I said, not only did they not have vectors, they didn't even have the word vector or any meaning of it, but forces were still relevant as not only a mattering how big the force was, but also mattering in what the direction of the force was. So there's a lot of sentences that go on with it, but basically what he said was that the force due to gravity, which I'll call F sub g, is directly proportional to the product of the masses. In other words, he's saying, hey, any two objects of mass m are going to have a force of attraction, and it's only a force of attraction. It's never a force of repulsion, unlike the electric force and the magnetic force. It's only a factor, only a force of attraction. And because of the analysis he did comparing it to the moon's acceleration, he knew it was inversely proportional to the square of the distance between them. And of course, from your Algebra 1 days that in order to take an expression from directly related and inversely related to an actual equation, you have to add a constant. So what was added was a constant called the gravitational constant of the universe. And the law became G M1 M2 over R squared. And there really should be a diagram that comes with it. So I'm going to sort of give you a little bit of a diagram. So you can imagine just a point, coordinate system sitting in space. You can imagine, for instance, a point particle M1 and another particle again, just a point particle, M2. And what you do is you imagine the line connecting those two. And then you'd say, okay, if you want to know what the force is, the force on 2 is parallel to that line. And we'll call it F2(1), which means the force on 2 due to mass 1 is G M2 M1 over R squared, where we're going to say this distance right here is R. Okay. Similarly, we could say, for instance, also parallel to that line, but in the opposite direction, is F1(2), which is the force on 1 due to 2. And that's, of course, G M1 M2 over R squared. So notice with those sentences, we actually not only have a formula to calculate the magnitude, but we also have a way that's prescriptive and allows us to discover the direction. The direction is along the line that connects the 2 point particles. But if they're not point particles, it gets a little more complicated. But in this class, you're only going to calculate it from a specific point. So like they'll say, 2 planets, and you basically calculate it from the center of one planet to the center of the other. And that's basically correct unless the planet is, not necessarily spherical symmetric. So if you imagine a planet made of marshmallow, but then, halfway between the center and one point on the edge, you stick in there a lead BB, well, that's going to throw it off and make the center of mass not be exactly in the center of the sphere. So really the bigger thing is you've got to go from the center of mass of M1 to the center of mass of M2. But in this class, you're never going to have to calculate what that is. So I'll just tell you so you'll know, it's generally that the force is always attractive. I have the same problem. It's always attractive and acts along the line connecting the 2 point charges M1 and M2. If they are not point charges, then it points along the line connecting their centers of mass. So you could imagine, for instance, a blob of mass M1 with a center of mass right there, and a blob of mass M2 with a center of mass right there, then it would be along that line. Okay. Everybody understand that? Does that make sense? So that's Newton's law of gravity. Now, the way they were able to determine that, and specifically determine that constant, is they used a neat little mechanism. I'm going to go ahead and give you what the constant is right now. G is equal to 6.67. I actually should give you another sig fig. Let's say gravitational constant. Let's see if I can get a more than the sig figs I have here. 6.674. That's good enough. 6.67. It's actually 67430 times 10 to the negative 11th. That's Newton's meters squared per kilogram squared. Now, how they did that is this. Now, you've got the number. This, obviously, these notes will be posted right after class on my Google Docs, so you can access them there. But the way this was actually done is you can imagine, for instance, taking a mass, and let's say two spherical masses. That's really what was used, like so. And they would ideally be identical, but they're connected by a rod of some sort, like this. And then there was another mass and another mass. I'm trying to move this. Okay. So there's a mass and another mass like this. And then what was used was a sort of flat ribbon that, if we look at it from above, the flat ribbon, if we look at it from above, the flat ribbon would be attached at the middle and would be shaped sort of like that. Because it turns out when you take a piece of flat ribbon like that, the amount it rotates is directly proportional to the angle through which it rotates. So you can use that mathematically. And what you'd know is this one would be like M1, and this one would be, excuse me, and this one would be like M2. And then this one would be, of course, M2, and then this one would be M1. In other words, if you could actually use fairly identical masses, then you know each of these has a force given by G M1 M2 over R squared, where R is the distance between the center of masses. And you could use the rotation that this goes through to cause it to be attracted to this blue mass that's sitting on a pole and this other blue mass that's sitting on a pole. And that torsion balance, which is what we're using here, it's a torsion device, that was allowing us to figure out what the actual constant G was, and it allowed them to test to make sure, hey, what if I double M2? Is if I double M2 on both ends of that rod, is it going to double the force? And it turns out it does. So on and so forth. So that's actually how it was done. We now know, of course, that the gravitational acceleration is given by that. And just for the record, it turns out that the Coulomb force, which is the force due to the electric charge, that can be attractive or repulsive, but it looks like this. It's the product of the charges Q1 to Q2 instead of the product of the masses, and it's inversely proportional to the square of the distance between them. And check this out, this K is actually 8.99 times 10 to the positive 9. That's Newton's meters squared per Coulomb squared. So you can see if you just divided K by G, you'd get K is roughly equal to G times 10 to the 20th. But in fact, if you actually try problems, like if you calculate the gravitational attraction between the proton and the electron in a hydrogen atom, and then calculate the electrical attraction between them, and then divide the electrical attraction by the gravitational attraction, you'll find that the force electrical between the proton and the electron divided by the force, divided by the force gravitational between the proton and the electron is on the order of 10 to the 42. So it's quite a bit even bigger than 10 to the 20th. Okay. Any questions on that? Yes, Brandon.
I had a question about the gravity of the moon that you had put like, up.
Right.
Um, so are you saying that the gravity at the moon is the gravity of the Earth divided by 3600?
Yeah, the acceleration that the moon has to have to actually go in that circle turns out to be exactly the same as 9.8 time divided by 3600. It's roughly
Oh, I
0.0027.
see. Okay. I
My
wasn't sure if you're
calculation was threw together, so it didn't come out exactly, but his calculation worked out perfectly.
okay, I see. Thank you.
No problem. So yeah, imagine what a eureka moment that is. You do the calculation v squared over r, and you get a number, and then you take 9.8 and divide it by 3600, you get the same number. You're like, wow, that's pretty awesome. And that's what Newton did. And it's also the reason, or one of the reasons, and probably the first one, why Hooke and Newton didn't get along, because Robert Hooke had claimed that he had performed the exact same calculations and knew this stuff. But no one ever got him to release those calculations or even let them see them. He claimed he'd do it. He claimed he would give them to him. He never did. Newton, in fact, did redo them again and turned those over to his friend Edmund Halley. And of course, everybody got to see it. So Newton is definitely credited with the universal law of gravitation. Now, it's called the universal law of gravitation for a bunch of different reasons. I should probably write that down. I'll write that down here. Universal law of gravitation. And it says universal for a couple of reasons. One thing is it applies to any two masses. So if two things have mass, then you can find something that seems to behave like a force, and that magnitude of that force will be given by Newton's formula by multiplying the two masses together and then dividing it by the square of the distance between them, and then multiplying that by 6.67 times 10 to the negative 11. So it's universal in that it applies to every mass. But if you look at it, can anybody think of an R value that you could put in Newton's law of gravity that would give us an actual zero for the force?
Infinity.
Yeah, infinity. So what that tells us is that the gravitational force actually reaches entirely out to infinity. So it reaches across the entire universe. So that's another reason we call it the universal law of gravitation. Okay. Now that's a big deal. And in fact, we do have to do corrections. Probably you all know that Einstein rewrote this in 1915. So in 1905, he did special relativity, where he was basically attacking all problems that were in what's called inertial reference frames. And what he meant by inertial reference frame is anything that appeared to obey Galileo's law of inertia or Newton's first law of motion, which says an object in motion tends to stay in that state of motion unless acted upon by a net external force. Well, if you look, for instance, at the moon orbiting the Earth, you cannot see any forces pulling or pushing on the moon, yet the moon is accelerating. Its velocity is changing. It's accelerating towards the center of the Earth. Therefore, that's a non-inertial frame. That's what Einstein was using to say, hey, I'm ignoring gravity, because he's treating gravity as if it's not really a force at all. It's got to be something else. And that's also like when I was telling you about how to draw your free body diagrams. I said, you look at the body that you're trying to draw a free body diagram for, and you look at everything that's touching it. And everything that touches it has the ability to apply a force to it. So you go ahead and write down those forces in the free body diagram. But then I had to give you that extra rule that says, okay, now that you've done that, now if there's a gravitational force on it, you need to add that, because you know, the Earth doesn't have to touch your body, your object, to have it apply a force to it. And the same thing with the electrical force, and the same thing with the magnetic force and the nuclear forces. So that's basically what what Einstein was doing, is he said in an inertial frame, the laws of physics are the same. and that's that's Einstein's special theory of relativity. And then his second rule is that the speed of light is a constant independent of the motion of the source and the motion of the observer. Now, in 1915, he had finally figured out gravity, and he published a paper. And in that paper, basically, he said that one, he could calculate the actual precession of the perihelion of Mercury. So it turns out, if you were to, for instance, look over a long period of time, you would say, okay, this is the sun, like that. And then you'd say, okay, and I'm going to draw Mercury's orbit as if it's way more elliptical than it is. But that's sort of, let's say, the orbit of Mercury. And what we knew already was the planet Mercury had a precession of the perihelion. The perihelion is really this spot right here where the planet is closest to the sun. And what they were saying precessing was basically when the moon got back, or when when Mercury got back here, it would trace a slightly different path, like a spirograph, and then a different path, and then a different path, and then like that. And they had Einstein had used his general theory of relativity to calculate that this was, and I'm completely making this number up. I don't remember the number off the top of my head, but I just want to give you like a ballpark figure. So let's say it's like 0.3 arc minutes per century. Okay. And Einstein put that in the paper in 1915. 1915, there was some stuff going on in the world. Does anybody know one of the things that might have been going on in the world?
You say 1950?
1915.
Oh, like World War One?
Yeah. So they had several expeditions planning to go out and check Einstein's other corrections. So Einstein got this value right on the money, and that fit experiment. So he already had one experiment that explained something in nature from his general theory of relativity. But the other thing he said is go out and look at it during an eclipse and find a star that's otherwise supposed to have it be lined up right along the edge of the sun, or maybe even behind the sun during the eclipse. And you'll see that the starlight from that star is coming from the wrong space, or the wrong point in space. And he calculated exactly what angle that would cause that light to go through. As luck would have it, he'd made a little careless error and was off by a factor of 2. But luckily, because of the tragedy of World War I, there was literally one mission that went, I think, somewhere, is either South America or Africa or somewhere like that. But there was literally like cannibals that had captured one of the expeditions and held on to them, so they didn't get to do theirs. A couple others got shot down by I say shot down, as metaphorically got shot down by bad weather. And then another group was captured by combatants. So luckily, none of that measurement was made in that first eclipse that happened after 1915. But that gave Einstein enough time to find his error, and he went back and corrected it. And then by that time, another eclipse was coming. Sir Arthur Eddington, the Astronomer Royal for Great Britain, actually did it. And he measured it and found it was right on the money. And it was a really big deal because, like the New York Times said, God said, let there be light, and Einstein told it how to move. So it was really an appreciation for how big of a deal this was. Imagine this guy just used his brain with no evidence to suggest anything was wrong with anything, just conjured up a new way to think about gravity altogether, and got an answer that predicted a very distinct thing that we had never seen before. And lo and behold, he was right. That's a really big deal. That's the holy grail for a theoretical physicist. So it was a big deal. And in fact, Einstein got to go touring. He, at one time, in fact, his biographer, I think Walter Isaacson, wrote the most recent biography of Einstein. And it evidently he had at one time 12 women at one time as girlfriends he was dating. So I remember Jay Leno saying, God, he must have been oh yeah, it's Einstein. Yeah, he was a genius. So if you can imagine trying to juggle 12 women, that would be pretty problematic. Or 12 spouses of any sort would be problematic. But anyways, he was quite famous. He went on tour. He's not that handsome of a dude necessarily. So you got to say it must have been the science or something that made him attractive to people, and the fame and all that good stuff. But when he got to Great Britain, they were clearly fishing for him to give a compliment to their astronomer royal. And they asked Professor Einstein, what do you think about Arthur Eddington? And Einstein said, well, he's a good enough fellow. He's a nice man. And I like him. And he's a smart fellow, but he's not a very good scientist. And they were like, what? He said, well, he's not a very good scientist because when he was testing my theory, he stayed up all night worrying about it, working hard, analyzing the data and all this stuff. However, I slept like a baby because I knew if I was wrong, God was wrong. And that sounds extremely sacrilegious, and in some sense it would be, but you've got to understand what Einstein's version of God was. Einstein believed and repeatedly said, I believe in the God of Spinoza. So if you look up Baruch Spinoza, Baruch Spinoza, Spinoza, you'll see there's a philosophical definition of God that he employs, and it's sort of like our idea of Mother Nature. Okay. And it's essentially impossible to disprove its existence. So Einstein's saying more like, hey, I believe the universe is this beautiful place, and my general theory of relativity is the most beautiful version I could imagine to explain the universe. Ergo, if it's wrong, then it's just can't be right because the universe is beautiful. So that's sort of what Einstein was saying. But it is kind of funny because he was asked about all sorts of stuff. They asked him, Professor Einstein, what about this ESP and telekinesis and stuff like that? So he's talking about, the ability to read minds and whatnot. And he said, well, if you show me it obeys a 1/r² law, then I'll believe it. So that tells us something pretty deep. That tells us that the 1/r² law obviously has some deeper meaning. You've already heard today that Newton decided to use it when he considered gravity force. And the reason why is because he had been studying light, and he knew, for instance, if you had like a candle, or in our times we'd use like a light bulb or something, but if you're 1 meter away from the light bulb and you measure the amount of energy landing on a 1" by 1" square, you'll get a certain value. But if you move that, instead of being 1 meter away, it's now 2 meters away, you'll find out that that brightness is now 1/4 as large as it was at 1 meter. And if you moved it to 3 meters, you'd find it's 1/9 as large. So that again suggests something deeper about the 1/r². So let me give you a little taste of what that is. So when he's talking about ESP, he's talking about a human brain having some ability to either send out waves that someone could read, or someone could send out their brain waves in such a way that they could read someone else's mind. And in either case, if you're really talking about significant distances, the size across the brain is infinitesimal compared to how far away you are from another person. So it's really like the brain is a point object. So let's imagine for a second that a light source is a individual point like this one. Okay, now that's supposed to be a circle, and it did not turn necessarily into a circle, but it's close enough. So what I'm going to do now is I am going to draw a sphere that should be ostensibly centered on that. So that's supposed to be a light, for instance, like a small light bulb. And then it's surrounded by a large sphere, if you will. And I'm trying to center it up as good as I can now, too. That looks pretty good. I can do it that way and that way. Yeah, that looks okay. So let's imagine, for instance, this is a sphere that's 1 meter away. And now I'm going to draw another sphere that's 2 meters away instead of 3 meters away, like that. So I'm saying this distance right here is 1.00 meters, and this distance right here is 2.00 meters. Now, what I'm going to do is I'm going to imagine on this inner sphere, there is a window through which a certain amount of light has gone through. So this light is sending out a little beam of light that way, that way, that way. And actually, this one should have been drawn a little better. Let me fix that a little bit. So this light came from here, and then this light came from here. Okay. Now let's say, just for the heck of it, that I measured the amount of energy coming through that window. And through that window, there was, in fact, let's say 40,000 joules per square meter. And the reason why it's per square meter is because this window is 1 meter by 1 meter. Now, if you take that exact same cone of light, if you will, and continue it on to the next shape, to the next sphere, like this, then simple geometry tells you that that window would in fact be 2 meters by 2 meters. And since only the light that came through the black window came through the blue window, then you know the energy coming through this one will be 40,000 joules, again, because that's how much went through the first window. But now it's 2 meters times 2 meters, which would be 4 meters squared, which equals 10,000 joules per 1 square meter. That's exactly why we expect things to obey a 1/r squared law. Does that make sense to you guys? All right, so that's something you could play around with or think about, whatever you want. The main thing, like I said, is if you're talking about something acting at a distance and it's something really small compared to the distances away, then it's not unreasonable for it to behave like a 1/r squared. In fact, it turns out that radioactivity, if you have a small source of radioactive material, then that small thing, if you go a far distance away, let's say a factor of 10 or 100 times its size away, then what you're going to find is the radiation dose you're going to get from that at 1 meter will in fact be 4 times as big as the radiation dose you get from it at 2 meters. And it would be 9 times as big as the radiation dose you'd get at 3 meters, and 16 times bigger than what you get at 4 meters, and so on and so forth. So that's just something that happens over and over and over again. It happens with light. It happens with sound to some extent. It's harder for us to hear because we have a logarithmic response to our ears have a logarithmic response to sound, but the actual energy delivered does go like 1/r squared. Any questions on that? Okay. So you can quickly do things like what's the force of attraction between the Earth and the Moon? So force of attraction between Earth and Moon. Well, all we have to do is solution. We know the formula, so and they're just asking really for the magnitude here, so that's really all I need. So the force of attraction between the Moon and the Earth is going to be 6.67. What did I find? 6.674, I think, was the next digit. Yeah, 6.674 times 10 to the negative 11th newtons meters squared per kilogram squared. That's the G, times the mass of the Earth, which is 5.972, times 10 to the 24th kilograms, times the mass of the moon, which is 7.347, times 10 to the 22 kilograms. And then all of that will be divided by that figure I gave you, which was essentially the average distance between the Earth and the moon, which was, I wrote it up here, 3.826 times 10 to the 8th. So 3.826 times 10 to the 8th meters. And of course, it's distance squared, so it'd have to be that. So when I do this calculation, you can say 6.674 e to the negative 11 times 5.972 e to the 24 times 7.347 e to the 22 divided by, now I'm going to put parentheses, 3.826, and that's e to the 8th. I'm going to square that and then close my parentheses. Ah, crap, I hit a parenthesis. Oop. Sorry about that. I have to type it all back in again. 5.972 times 10 to the 24th, 7.347 e to the 22 divided by, divided by parenthesis 3.826 e to the 8th. Now I'm going to square that, close parenthesis, and this gives me 2.000, so a plenty of digits there, 2.000 times 10 to the 20th. Notice the Newton meter squared per kilogram squared. The meter squared cancels out with the meters in the bottom squared. The kilograms cancels out with the kilograms in the top squared, and we're just left with newtons. So that's how big the force is. Now you can also say, what about between, let's say, the sun and moon? There's actually a reason I'm doing this. Okay, so the force of attraction in this case is equal to 6.674 times 10 to the negative 11th Newton meters squared per kilogram squared. And then I got to take the mass of the moon, which is 7.347 times 10 to the 22 kilograms. And then I got to take the mass of the sun, which is 1.989 times 10 to the 30th kilograms. And then we're going to divide all that by basically an astronomical unit, because an astronomical unit is so much bigger than the distance between the Earth and the moon that really it's not going to matter too terribly much. If you wanted to, you could actually subtract out the radius of the moon and then consider when the moon is closest to the sun by doing that. But I'm just going to put in the distance between the Earth and the sun on average. So the Earth's orbit has a radius of 1.496. I think that, yeah, 1.496 times 10 to the 11th meters. And that's going to be squared. So 6.674 e to the negative 11 times 7.347 e to the 22 times 1.989 e to the 30 divided by parenthesis 1.496 e to the 11th squared, close parenthesis. This gives me 4.358 times 10 to the 20th newtons. So you see that actually the force that the sun applies to the moon is about twice as big as the force that the earth applies to the moon, at least in that particular configuration. I actually thought it was the other way around. I thought it was, in one case it's 2, in the other case it's 4, but I thought the attraction between the earth and the moon was bigger than the between the earth and the sun. I mean, between the moon and the sun. But anyways, there's some calculations. Anybody have any questions on that? All right, so that's the way you calculate that. Of course, you can also make it vector quantities. So you can do crazy stuff like let's draw a little coordinate system just for the heck of it. The coordinate systems are nice in that you can definitively say exactly where something is, and everybody understands you. So that's why I'm liking doing that. So we might actually say, let's put a mass right here. And let's say that mass is m, and we'll assume it's like a point mass, so you don't have to worry about its size. We're just going to say its center is right there on the x-axis, like that. And let's say that mass is equal to, let's say, 300.0 kilograms. And I'll call that M1. And let's say I've got another mass right here that is 100.0 kilograms. And I'm going to call that M2. And then I'm going to say there's another mass right up here, and that's M3. Whoa, Nelly. And that's M3. And I'm going to say that one is 200.0 kilograms. Let's say this one is in fact 4.00 meters. This one is at 3.00 meters, like that. And what I want to know is what is the total force on M2. Okay. Solution. F2 total, which I can just call F2, is going to be the force on 2 due to 1 plus the force on 2 due to 3. Okay. Now, what I have to realize is the force on 2 due to 1 points this way. That's F21. And the force on 2 due to 3 points this way. So that's F23. Okay. So these are vectors, and I'm going to have to compute their magnitudes, but then I'm going to have to treat them like vectors, not just scalars. So I can now say F21, oops, go back to blue. F21 is equal to 6.67. I'm going to leave off the units this time, e to the -11th. Oops, I don't like writing it that way. Times 10 to the -11th. I'm going to say 2 and 1 obviously is 100.0 kilograms times mass 2. Well, that is mass 2 times mass 1, which is 300.0 kilograms. And of course, the distance in this case is really simple. It's 4.00 meters. I'm going to square that, and I'm going to say 6.674 e to the -11 times 100 times 300 divided by 4 squared is 16. That gives me 1.251 times 10 to the negative 7th newtons to the right. So you could actually say that F21 is equal to 1.251 times 10 to the negative 7th newtons in the I hat direction. F23 is equal to 6.674 times 10 to the negative 11th. Again, I'm leaving the units off, even though I forgot about the kilograms and meters last time. Again, mass 2 is 100 kilograms. But this time mass 3 is 200 kilograms. And again, I put the kilograms up there like a goober. And this time they're 3.00 meters apart. So I'm going to say 6.674 e to the negative 11 times 100 times 200 divided by 9. That gives me 1.483 times 10 to the negative 7th newtons, and that's upward. So you could also write F23 is equal to 1.483 times 10 to the negative 7th newtons in the J hat direction. And then therefore F2 is equal to 1.251 times 10 to the negative 7th newtons in the I hat direction plus 1.483 times 10 to the negative 7th newtons in the J hat direction. You can see that's also using the Pythagorean theorem. I'm going to go 1.251 squared plus 1.483 squared. And then I'm going to take the square root of that. And I'm going to get 1.940 times 10 to the negative 7th newtons at. Now, I have to take the inverse tangent. So I'm going to say tangent inverse of basically the F23 force divided by the F21. So the F23 force is the 1.483. So I say tangent inverse 1.483 divided by 1.251, close parentheses. And that gives me 49.85 degrees. So what that means is obviously this force is a little bigger than this force. So the net force acting is that way. And this angle right here is 49.85 degrees. And this magnitude right here is 1.940 times 10 to the negative 7th newtons. Any questions on that? So that's sort of the easiest scenario. Now, what I want to tell you about, and you can read the history or you can watch, I have a scientific revolution video on my YouTube channel. I highly recommend you watch it. It tells you the history of Brahe and Ptolemy and Aristotle. So I'm just going to say, watch Copernican or scientific revolution on my YouTube channel. But suffice it to say that there existed in the times of ancient Greece this people that paid attention to things day in and day out realized that there were certain patterns in the night sky that you would see over and over again. That means like if you went out at night, right now in October, you might see a pattern of stars that looks like this, which I call sort of Homer Simpson's shoe, if you will. You would see this pattern of stars out there. But if you came back in, say, January, well, yeah, January would be good, or June or something like that, you wouldn't see that pattern. But if you came back again in early October, you'd see that pattern again. And that pattern, if you watch it overnight, it looks like it would rise and go up and to the right, up and to the right, up and to the right. It would reach its highest point due south of us, and then it go down and to the right, down and to the right, down and to the right. So it really felt like the world was sort of centered on us, like the universe was set on us. And because of that, they imagined that there was a giant crystalline sphere centered on the earth, and that crystalline sphere had little holes in it. This is actually one of the many ways that they came up with the idea of what the stars were, but there were little holes in that crystalline sphere, and outside of that crystalline sphere was nothing but fire. So you were seeing the flickering of the fire through those little holes, and because they were holes in basically rock or stone, they didn't move with respect to each other. That explained why you saw the same set of stars every October, because that just happened to be the set that was visible at the time. Now, in addition to that, every now and then they'd see, let's say, a constellation that looked like this. I just drew this one again, but you can do like this as well. This constellation's Gemini. You can see it sort of looks like a twin because it looks like that top diagonal looks like a mirror image of that bottom diagonal. But what would happen is every now and then you'd look at it in, say, December, and you'd see this bright spot there where it wasn't before. And if you watched over a couple weeks, it would do like this. And then it would start getting really, really bright. And then it would go back to like it was and do this. And in fact, the path it took was like this, and this part was called retrograde. So those things appeared to wander through the star patterns. And they named them wanderers. And the Greek word for wanderer is planetos. And that's how we got the planets. Now, they left something to be understood, but by the time of Aristotle had worked out basically everything in some sense. And he deemed that the heavens, being the fifth element, were the quintessence, and they were perfection, and they were immutable. So you couldn't have things change. That means they always had to go the same speed and always in the same direction. They never sped up or slowed down. Of course, it's obvious that the perfect shape is the sphere. So everything in the heavens has to be spherical, or if it's not three-dimensional, then you could settle with a circle. But basically, because of that, they came up with a Ptolemaic / Pythagorean / Anaximander / so on and so forth. Various people, both before and after Aristotle, had come up with patterns of more crystalline spheres in which were embedded the planetos. And ultimately what they had was an idea that in the center of the universe was the planet Earth, and then orbiting it, of course, was the moon. Okay. And then outside of that was the orbit of Mercury, but Mercury had shown us something very odd. Mercury and Venus both had, so this was the sun. And you could imagine, for instance, there being an imaginary line that connects the center of the sun with the center of the earth. Now, what they did to explain this behavior of Mercury is Mercury basically never got more than, I can't remember the angle, I'm going to make up something, let's say 27 degrees from the sun. So the way they explained that was there was a deferent, which is this circle. And then on that deferent was an epicycle. And this would be what Mercury was on. And then you could adjust, of course, the radiuses and that sort of stuff. But the main thing is for Mercury and Venus, the center of the epicycle was actually on this line connecting the sun and the earth, because that explained why Mercury wouldn't go more than, say, 27 degrees away from the sun, and Venus would only go like 42 degrees. So they explained that by putting these epicycles. So this one would be Venus, for instance. But again, the epicycles were on deference as well. And then you had epicycles on the outer planets too. So like Mars would have that. And what they were using is when the planets would come along this side or over here, that was when they were in retrograde. And notice that's when they are closest to the Earth, and therefore explained why they got brighter when they were going backwards. So what they would do is go ahead and take all the data, and they had data from literally almost 1,000 years BCE. They had data, and they would basically make the rotation rate of the centers of the epicycles and their radiuses match the data that they had seen. And then they use that data to run the model out forward in time, 5, 10, 15 years. And then they would publish this almanac, and this almanac would tell religious leaders and government leaders when good decisions were to be made, because at that time they didn't realize astrology was a pseudoscience. So they used the stars to make indicators of what they should do. Is this a good time to marry? Is this a good time to go to war? Is this a good time to make a deal of peace with some foreign country? All those decisions hinged on the astrological signs, and they use these models to do that. Plus they use these models to model, for instance, when the moon would be full, because there's certain holidays that relate to the full moon, for instance, Easter, or Saturnalia basically refers to a time in the year every year that ultimately turned into what we now know as Christmas. So we have all these different things, and that's how they had done it. The problem was it was really, really complicated. And in fact, Kepler said, had I been around, I would have asked God not to make this so complicated, because they had a system of, like, I think it turned out to be like 84 circles on circles on circles. And you had epicycles and deferents, and then they had equipoints, where basically you have to get next to the Earth in the equipoint, and only from that equipoint would a particular planet be moving at a constant speed, and it'd be a different equipoint, say, for a different planet or some stuff like that. So it was just ugly. In comes Copernicus, and Copernicus I do not consider part of the scientific revolution, because he basically said, hey, I think we've lost our way from what Aristotle taught us. He wasn't using any new data. He wasn't using this new scientific method where you do experiments or anything like that. He just said, hey, Aristotle taught us what to do, and we've sort of lost our way. Let's do that. So he literally says, when I took the Earth out of the center and put the sun at the center, then Mercury, which has the shortest period, obviously became the planet that was orbiting closest to the sun. And then Venus, the second longest period, or second shortest period, would be second farthest from the sun, or second closest from the sun, I should say, and so on and so forth. But he had all circular orbits, and the planets never sped up or slowed down, because he was trying to stick to Aristotle's ideas. That's all well and good. In the meantime, a brilliant mathematician was, boring the crap out of his 8-year-old students who he was paying to being paid to tutor, and he's teaching them, basic mathematics and stuff like that. And he gets off in a sidebar talking about how the perfect solids that we know of in the universe is exactly the right number of perfect solids to separate the individual planets from each other by a perfect solid. So he started working on a model of the universe, suggesting that instead of just celestial spheres, the celestial spheres were separated by these perfect solids. And he sends this paper out to everybody. Well, one person who gets it is sort of a Russell Brand type character, a guy by the name of Tycho Brahe, who's from a Dane. He was from Denmark. He had, in fact, once challenged a gentleman to a duel as to fight for who the best mathematician was. In the process, he got his nose cut off. So now he wore a prosthetic nose made of silver and gold that he stuck on a gaping hole in his face with basically wax. And he partied all day. And in fact, he was nobility. And I don't know if you know this, but one of the things about nobility, for instance, Kate Middleton, she doesn't poop or pee, and neither does, at least Meghan Markle used to not, stuff like that. So that's what Brahe did one day while partying. And in the process, he held his water too long, and he ended up, his bladder exploded, and he died a horrible death due to sepsis of his bladder. In that intervening time, though, he had hired this guy Kepler to put his model together. Now, Brahe's model, he was just not mathematical enough to figure out how to do all the work, but his model was the exact same as the Ptolemaic model, where basically everything is orbiting the Earth. But the only difference was he then had the Earth orbiting the sun. That was Brahe's model. So Kepler gets hired. They don't give him the data as quickly as he wants. Kepler is, or Brahe's, throwing parties. He's literally got a moose so drunk it fell down the steps and broke its neck and died. He had a pet human, which was what we'd call a little person nowadays. He was just a party animal. And then he'd stay up all night, measuring the stars. He didn't have a telescope. He had like a hole in the wall, and then he had like a really big protractor that would let him measure them very precisely. But he realized that Kepler might steal his thunder, so he was sort of doling out the data a little bit at a time. But quote unquote, luckily, when he died, Kepler managed to go get the data. His family fought him in court. He won the court battle. He got to finish his work. And he realized Brahe's model didn't work. The Ptolemaic model didn't work. The Keplerian model didn't work. Or excuse me, the Copernican model didn't work. And then the thing that he had come up with the perfect solids, that didn't work either. So he had to throw all of them out. And it came down to, do you trust Tycho Brahe's brilliant data, or do you trust the ancients? And he trusted, despite their differences, him being like a Mike Pence type character and Brahe being like a Russell Brand type character, he trusted Tycho Brahe and actually said there's no way that he made this big of an error, which was literally like on the order of 30 arcs of minute, 30 minutes of arc, excuse me. And in doing so, he said that the planets orbit the sun in elliptical orbits. That's his first law, with the sun at one focal point. And he said, 2, the planets sweep out equal areas in equal times. That's his Kepler's second law. And he found that the cube of the semi-major axis was proportional to the square of the period of the planets. And that was Kepler's third law. And at that point, you could use that model to make those almanacs again and get very precise data. And in fact, you could predict it hundreds of years in advance with no problems. And that was sort of could be a final nail in the coffin, except nobody was willing to accept it, because by this time, everybody had adopted everything that Aristotle taught and adapted it specifically to the major religion of the time, which was mostly Christianity, using our own Bible, which had been interpreted entirely in terms of Aristotelian physics. So it became a problem. That's it. We're going to do a couple more problems next time, but I've given you basically all you need to know to be able to do these problems. you can set G M1 M2 over R squared equal to MV squared over R. That actually will allow you to prove essentially Kepler's third law. Conservation of angular momentum will let you prove the second law, and conservation of energy will let you prove the first law. None of which are you required to do. I'm just saying we've got all the tools. I showed you how to work with the gravity equation. So I'll show you some more next time, but you guys are free to go, and keep an eye out for a new test coming up. Like I said, I'm going to make one, and you're going to have it due either either Sunday night of this week or maybe Tuesday night of this week. Have a good one, everybody. I'll wait for the last person to leave.
Oh man.
And I've got to fix that test. I did remember this time. That's good. So I just have to make it open again. No problem. Anybody have any questions?
Of course I do, but I'm just waiting till everybody leave.
Okay. All right. I got Sean Richard. I think that was Richard that was just talking to me. Richard's the one I've got to set the test up for. Josh, did you have anything, or Sean? I'm going to stop sharing now. I said, you've got enough of my personal information. I'm not sharing anymore. Something different. All right. So let me go in here. I am going to do this. Okay, Richard, do you have a camera on your computer?
Yeah, I got a camera.
I can let you take the online version if you'd like. You're just gonna have to have a camera on yourself, and there's all sorts of steps you got to go through. Like you got to take the camera and show me your workspace, show me down below your desk, show me your photo ID so I can verify it's you, matching your face, all that sort of stuff. But I can give you like up till let's say up until Sunday night to get it done if you don't mind.
All right, that sounds good. And I have another question about another assignment.
Gotcha.
It was Tuesday of last week, 26th. It's part 2, chapter 3 and 4.
Oh, gotcha. Yeah. So you're talking about test 2, chapters 3 and 4. Yeah, that was due yesterday morning, or excuse me, yesterday.
Yesterday morning. Hold on, I ain't seen nothing.
Yeah, it was 11:59.
Oh yeah, I did that.
You did do that one? Yeah, I thought you did.
But I'm saying there was 2 assignments that was like a week ago on the 26th.
Oh, well, the assignment might have been. You think it was something in MATLAB and mastering, or are you thinking about like an extra?
It was on Canvas, but I wasn't really sure what to do with it because what I'm saying, I didn't take the test yet. So.
Oh, gotcha. Yeah. So, so far we've done chapter 5. We finished that last week. Just now we did essentially chapter 6. So you can do those homeworks. You are allowed to do them late, but you lose some points for doing them late.
Yeah.
You've got the test 2 done. So I'm going to go ahead and set up test 3. You knock that out. It's going to be slightly different from the one other people took, but it should be substantially different.
All right. So what's this assignment that I'm looking at in Canvas that's due on the 26th of September?
Of September 26th. And is it this week or next week's? It looks like I see a February 26th. I don't see a September 26th. Let me see.
Can I share my screen?
Yeah, go for it. Let me turn it so you can.
All right.
There you go. You should be able to.
All right. What is it? Safari?
Actually, I'm going to go ahead and pause this.